Exercise 23. Prove that a joint pair is equivalent to the following information, following data. Suppose Fg is a joint pair of functors between category C and D. Recall that is the joint pair means that bifunctor is isomorphic as a functor to the bifunctor category C. G sends elements of C to elements of D to C. So this is bifunctor. Where you evaluate elements of C here and elements of D here, so it's a bifunctor over C product of D. And the exercise asks you to prove that this information is equivalent to the following information. Firstly, the morphism of functor from F composed with G to the identity functor over D as functor as a natural transformation. Sorry. So this is a natural transformation. Which means there exists such a functor eta. And secondly, there exists a natural transformation as called epsilon from identity of C to G composed with F, such that if you start with functor G, apply identity functor composed with G, give you a functor to GF composed with G. Well, if you think of this as G composed with FG, then through eta, this gives you back again to G. So this G of eta should be compositionals. So eta gives you a natural transformation from F composed with G to identity, and so G composed with this gives you a functor, gives you a morphism functor or natural transformation from G composed FG to G. Similarly here, if you got G, if you got your epsilon natural transformation from identity to G composed F, then G could also compose with it. require this to be the composition to be the natural transformation, the identity natural transformation. Similarly, if you start with F, you could arrive at GF. Go back to F. Require this again to be identity natural transformation of F. This is exercise. I'm going to prove this. Let's first, well, we'll not give all the detail. Let's, for example, let's first check. Let's just check this maybe. Given natural joint pair, you got the following data pair of eta and epsilon satisfying the following condition. Okay. So from the isomorphism of bifunctors, we have in particular for any morphism C, and any morphism D. This is isomorphism functor, so actually a natural transformation you could think about. So for any given morphism, we have a community diagram. F of x let's first evaluate apply this G prime. Firstly, we have this isomorphism. This is exactly the same isomorphism I wrote there. This is applying for x and y. Let's first focus on this part. If we apply this functor to y on the second position, then this got but this is covariant, so it doesn't change the direction of the arrow. It's the same as before, so it's just home. Prime G prime composed with this map. You start from a map fx to y and then compose with G prime, then you map to y prime. I don't know, maybe I could call this position, call it theta, call this gamma, and this is like I don't know if it's good to call it theta x, gamma y, and this is theta x, gamma y prime. x to gy, gy to gy prime, so this is composing with jj prime, jj prime. Yeah. Why bother calling f prime j prime? Let's just call it f and g. Okay, similarly, the first position you have control factor, so you got fx prime. This is composed with f, or more precise, ff. So this is theta x prime, gamma y prime. We got this commutative diagram. Okay, so more or less this is all what it is. Let's use this diagram to say that we could got those data. So let me make a copy of this. So what we do is we're going to take special x and y, and so that we got some bijection. This will help us to construct or find the epsilon and eta map. So look at this isomorphism in the first row. If we want to get epsilon eta, if you take y equals fx, then what you got is on the left hand side you have home set from fx to fx to, in particular you have identity. It corresponds to, on the right hand side, a morphism from x to g fx. And this gave you a factor eta from identity of C to GF as natural transformation. Let's just write it slowly. Basically, I only tell you I got morphism. I haven't really checked its natural transformation. So we got from this first row. Right, so particularly here you have this identity, and so this is bijective to some element here, and let me call it epsilon. And you have to check that this epsilon corresponds to or this epsilon defined by this bijection. So a priori this is at this moment just a functor from identity C to G composed of F, a map from identity of C to G composed of F. You haven't checked its natural transformation, okay? You have to check that. Similarly, if you take x equals gy, this will give you a map eta. And again, the true transformation. Let's check it. Is indeed a natural transformation. So let's take arbitrary map in category C, and they want to check the epsilon we define as natural transformation, which means if you apply this epsilon to this morphism x to x prime, so on the left hand side you have x to x prime, here you have your G composed of fx epsilon x, here you have your epsilon x prime, G composed of fx prime, and the question is this commutative, right? So prove this is commutative. So let's go back to this bigger diagram. So what we have, you got this in particular. If you use this disjoint or this isomorphism bifunctor comes from this adjoint pair, you got so basically for this second position we are using this map, and so we rewrite this big diagram here. Correspondingly, for the first position, which is a contravariant functor, we also have this Quadratic diagram. So here we are applying to the second position the morphism. For the first position, we took just this is horizontally we are applying. Just replace y with fx. Vertically, what we are doing is instead of applying to the morphism y to a prime, we're applying to this ff, and then we're looking at the first position instead of applying to the morphism. Fx prime to fx, we're applying it basically that's the only thing we changed. So here, all those what we have done here, we only replace this by fx to fx prime ff. That's all what we have changed, and everywhere else is unchanged. But this tells us the identity fx, this is mapped to how we define our epsilon, right? Identity corresponds to epsilon. Epsilon is a map from x to gfx. More precisely, should we denote this by epsilon x? This is the same as epsilon x here. It's the same as epsilon x here. Okay, so here is mapped to G, compose F, compose small f, then epsilon x. Or you can write this, which is exactly the composition of this two. And then here, this is just f. And this also corresponds to the identity fx prime. This is computer diagram, so this is mapped to that, okay? But this also maps to F. Sorry, this is the vertical line F, so this one is again epsilon fx prime. Epsilon x prime. And this is mapped to here by composing with F. Which is exactly the composition of these two arrows. And so they must be the same. And so we prove the naturality. Very complicated. Finally, so that for the eta you could check similarly, but still left to check. You have this composition called identity. We still have to use particular choice of x and y in this commutative diagram. In case we have this following commutative diagram. Actually, we're considering this morphism. So Fg y is object in category D. Fg, F composed with G, is also functor over D. From D to itself. This is in D. Eta is from Fg to identity, so eta composed with Y. Or eta evaluate on Y if you want. It's natural transformation, just I write it like this. Then got this. So we're taking x to be gy, y to be fgy, and apply it on the morphism from fgy to y. Then this is a covariant functor, so you got this. Similarly, this side is J eta y. JY, JY. Suppose isomorphisms. So J eta Y well still SU. So identity here FGY corresponds to epsilon GY, and here it maps to eta Y, right? And this is mapped to what? Yeah, eta Y here. Wait. Yeah, this is eta Y. This corresponds to identity of GY. And so this is telling, the commute diagram is telling you that J composed eta Y composed with eta JY equals identity of GY. This is what we want to prove. J of eta composed with epsilon G equals identity. A little confusing about the notation. Am I correct to write this G without, should I write this? Wait. Also here I'm writing epsilon of x. Epsilon of x is okay because x is the object. But here G of y is object. Yes, I could write epsilon G of y, but I think maybe this is also the same as epsilon composed with G and then you write y. Yeah, I think it's the same thing. Yeah. You see what I'm saying? That if you have a natural transformation, this is theta from F to G, then can you compose it with another functor? If it makes sense, of course. H and check that this is again natural transformation. Basically this is okay because it's just whatever you evaluate. It's just f some object, G applying on the same object, and then theta corresponding to the same object. Yeah, so basically, how do you understand this notation? You could read this as epsilon composed with G. Or it doesn't matter if you write this. I think it's the same thing.